In the previous segment, we developed an analytic formula. However, that does not enable visibility, it does not enable emission, it does not enable non-Lambertian BRDFs. In this segment, we will develop a general Monte Carlo solution for rendering direct lighting with area lights. The first thing you notice is that we have put in this visibility term. Therefore, what we will do is shoot a number of rays to the area light and effectively average the visibility. We are multiplying by the BRDF, the surface normal, cosine term, and the visibility term. We will also enable a non-Lambertian BRDF. Here is the specular component of the BRDF, in addition to the diffuse or the Lambertian BRDF. This is really a Phong type model where you are considering the R dot omega in term and raising it to some power S for the Phong shininess. One thing we have to consider is that we have to integrate over the area of the light source rather than over angles. This requires a change in measure, which is the same as what we saw in the rendering equation. Specifically, the solid angle d omega in is given by the normal of the light source now, dot product with omega in, and make sure the signs of these things are correct. The homework goes into some detail in it. You don't want negative light energy. Divided by the square of the distance between the point x on the shading surface and the point x prime on the light source, times the differential area element on the light source. So the integral that you will ultimately have to solve is very similar to what you did for the rendering equation. Specifically, there is a geometry term between x and x prime, where x is now the shading location or the pixel that you are shading, and x prime is the location on the light source. You're actually integrating over the locations x prime on the light source using the area measure on the light source. You have both a geometry term and a visibility term. The geometry term is the same term we derived in the rendering equation. It is a product of both cosines of incoming direction as well as outgoing direction from the light source, and the difference between x and x prime, or the distance between them, squared. Notice that you can apply this formula with any BRDF f. We have chosen a BRDF which is a sum of diffuse and specular components. For the numerical or Monte Carlo solution, you are evaluating that integral numerically. What you need to do is sample some number of points on the light source, some number of locations x prime, evaluate the integral for those locations. We discussed several different ways in which you can sample the light source. One approach is to do random sampling, where you just use your random number generator to pick a distance along AB, a distance along AC, and then combine them together. That will just give you a number of random samples on the source, but they will not be distributed evenly. Better results are obtained using stratified sampling. In this case, I have a 3x3 grid. So I divide the light source into a 3x3 grid, which is known as stratification, and pick a sample randomly in each of the 9 subsquares. The assignment explains the details of how you do it. So mathematically, you're picking a distance along the AB, along AC, and then you're adding these vectors together. Once you have picked points on the light source, you simply need to do Monte Carlo evaluation of direct lighting. I have written down the integral that we are solving again. You will notice that we are using Monte Carlo to estimate this area dA, but we have equal probability of sampling any point on the light source. So the probability which is important in Monte Carlo is simply equal to 1 over A. Remember that in Monte Carlo, what you do is you evaluate the function f, which is everything else in this case, and you divide by p. So if you divide by p, that involves multiplying by a, which is why we have this term multiplying by a. Remember that Li does not go into the integral and it can be taken out, and we divide by the number of samples n to normalize. Otherwise, the term inside the summation or the estimator is simply the BRDF times geometry times visibility, which is directly taken from the original integral. Notice that the BRDF term is, of course, evaluated at the spatial location x, but it also involves the omega in, or the incident direction of sample k. That's why I've said omega in of k, and of course at omega out, which corresponds to the viewing direction for the camera. Similarly, the geometry term I've evaluated at xk prime, and the visibility term as well. Here are some examples of results you will produce. If you pick one sample on the light source randomly, you will get a result that has a lot of noise. And this is expected. As compared to the analytic result, you will get a noisy solution in Monte Carlo. As you increase the number of samples to 3, the noise reduces. Remember, the variance in Monte Carlo goes down as 1 over n. If you increase the number of samples to 9, you can notice that the variance is reducing still further. And if you make the samples stratified, so you now have a 3 by 3 grid on the light source, then you will notice that the variance has reduced very significantly because of stratification, and stratification is an important technique for variance reduction. If you compare to the analytic result, of course, the analytic result has no noise whatsoever. And you can actually make this comparison to verify that your Monte Carlo rendering is doing a reasonable job. Of course, the goal is not to render scenes without any visibility issues. For the assignment, you will render including with 1, 3, and 9 samples. You can even try with 5 by 5 stratified. You can render with direct lighting only, so turn off all the recursive ray tracing features you have. This assignment should use the ray tracing only for primary visibility and for determining visibility to the area light source, but otherwise should use the direct lighting formulas. One challenge we had in developing this course is to develop an automatic feedback and grading system. Until your ray tracer and in CSE 167, we could just check the difference in images or a pixel difference. However, Monte Carlo introduces noise, and that noise depends on your random number generator. So the automatic feedback can't just be pixel differences. We have to consider the bias and variance. The bias is on average how far your result is from the true solution. The true solution is either the analytic solution if we can compute it, or a solution shooting thousands of rays per pixel to converge to the true result. Monte Carlo rendering should be an unbiased bias zero technique, so if on average you differ from the true solution, there's something wrong in your program. And the comparison to analytic should initially indicate whether you have issues with bias. However, we also compute the variance, which is the squared pixel error, and the root mean square error is the standard deviation. All Monte Carlo results will have some variance. If you're producing a result without noise, you've either discovered something truly exceptional or much more likely there's some issue or error in your program. Your variance may of course differ from the variance in the solution because all Monte Carlo programs are different and you cannot expect to match the variance exactly. But we have specified the algorithm to use fairly precisely, and so we bound the variance in your solution whether it closely matches what our solution does. The focus in this course is on being correct, not just producing a pretty image. It's easy to produce a pretty image which has a number of subtle bugs. You can submit to the automatic feedback system as many times as you want, and ultimately we hope you will actually get the result correct and produce results with the appropriate amount of Monte Carlo noise. Here is an example of what our feedback system looks like. These are the correct submissions, and therefore I'm just seeing black. But it's a very advanced system that I encourage you to test out. It's been developed by Andrew Bauer. And he has developed a way in which you can mouse over the feedback and you can set a sense of where the solution differs. So I would highly encourage you to make full use of the automatic feedback system. The bias and variance it prints out, but it will also tell you where there are errors and what the variance of the correct solution should be.